is biased towards more recent stuff.
But you need to.
Yeah, but you have to be able to use all of the tools that we've had before in order to do that. That's really what a lot of this was building up to this was, I'm just flipping through this, we covered quite a bit of stuff.
I can think of questions and nobody else.
Well, if you know, you'll have an opportunity. Yes?
Do you have like answer keys that you could post for the exams on the campus?
No. But if you have any questions from the exams that you don't know how to do, we can talk about them right now.
Nobody else has questions. I would appreciate looking at more of the B matrix stuff, because that, you know, we talked about it really quickly.
Okay, yeah. Let me find that section and then maybe we'll get a problem from that. Was it change of basis?
It was right after diagonalization. It was like viewing diagonalization as a transformation, and then it was like a little footnote at the end.
Which we did, right?
Hmm?
We just sort of did that. Oh, we really did do that with the example. We did that exactly. Right? So we had the T is reflection.
Oh, yeah, I know we did it yesterday, I just love to see another example of it.
Another example of this.
It doesn't have to be that form exactly, because that one was on the quiz too, and it seems like there's a pretty standard approach to that question, so if there's like another.
There's a standard approach to that particular question, but there are variations on this question, right?
Well, that's what I'm asking for.
Yeah, I get you. Okay, so do you know what section?
Not off the top of my head, it's the one right after diagonalization, maybe like 5.5 or something.
I'm looking at 5.4, and that's eigenvectors and linear transformations, and then we have,
Diagonalization, and then the one right after that.
yeah, the one right after that is eigenvalues and eigenvectors.
Right after diagonalization. Can I see the textbook? I might be able to.
Eigenvectors and linear transformations.
Yeah.
This is the one you're talking about.
Yes.
Okay. All right. And so I was looking at the chat. Linear transformations from V into V, and then linear transformations when we're in. Okay, let's just pick a problem from here. See, this is why. This is why you should. I don't know which one's the.
Well, it was like I felt like I did the practice problem ones that you like gave us, like, cause those were like pretty standard ones, like find the B matrix, or like if this is the diagonalization info, find that. And then that one was a lot more like involved, I felt like, so I guess something in between yours was, I can't really, think of one of those, but they didn't really have many of those, like the ones on the examiner's quiz and textbook. I can't think of one.
Well, let me see. I don't remember which ones I assigned.
There's always like 3 from the beginning and then 1 from like the teens.
I think I was in a cheap hotel room in Cleveland whenever I sent this out. So. All right. Let's try this one. And if it looks familiar, we'll either do a different one or we'll just get over it. Okay. So B is going to be 1154. And the first one says verify that B1 eigenvector of A. So verify that, and then B says find the matrix of 4. Oh, find that B1 is an eigenvector of A, but A is not diagonalizable. So does this sound like a good problem? Okay, both parts, or just the second part?
Well, this is all sounds good.
Okay, let's do it. So, it's a shame that there's not a, like a recitation section attached to 322. Well, yeah, it just, anyway, we don't normally have time to just, sit and work out problems like we do today. It's kind of a shame. So B1 is an eigenvector, but A is not diagonalizable. Okay, so how can I do this? I can find that it's an eigenvector simply by multiplication. So 1 minus 1, 1, 3. 1 equals 2. And so I'm going to call this lambda 1 is equal to 2. So the eigenvector associated with this is 2. Now, how could this not be diagonalizable? It could be not diagonalizable if this has a multiplicity of 2 and it's the only eigenvector. Or the dimension of the eigenspace is just one dimensional. So, let's see. How can I verify that?
I have to find the characteristic polynomial first, right?
That's one way to do this. So let's go that route. Actually, we know that the characteristic polynomial must have x minus 2 as a factor, or lambda minus 2. Let's, at least for the sake of practice, let's work this out. So 1 minus lambda minus 1, 1, 3 minus lambda, and the determinant is equal to 1 minus lambda minus 3 minus lambda minus negative 1. So this is lambda squared minus 3 minus 1, so minus 4 lambda 3 plus 4. And sure enough, we get this is lambda minus 2 squared. So we do have that this is a multiplicity 2. Now, what we have is a what am I trying to say? We have a two-dimensional space. We have multiplicity 2. And so if we had a two-dimensional eigenspace associated with this, then the eigenspace would be all of R2, right? And if it was all of R2, then no matter what we put in here, we would get 2 times that out. And that's not possible from this matrix. So that's one way of showing that it's not diagonalizable, is that it doesn't have a two-dimensional So, yeah, what's the other way? The other way was that we could take this two, or we could look at, a minus two I x equals 0. We could solve for this and see what the eigenspace is. So the solutions for x will be the eigenspace. And this is a certain amount of work also. But we have sort of an independent reasoning for why this is not diagonalizable. If it were diagonalizable, then in fact it would be a diagonal matrix itself, because it would be 2, 0, 0, 2. Because it's the only matrix that corresponds to multiplication by 2. Okay. I'm moving more room right now. So find the B matrix for T.
Is T like T of x equals x or something?
Sure. That's the only thing that makes sense, but I'm gonna double check. So yeah, in the problem it says T of x equals ax. So that's with respect to the standard basis. So I can think of this as taking, let's see, this is R2, and this is the transformation T, which is the same as multiplying by A. And then there's, this is in the B coordinate system. Instead of going this way, I'm going to go this way. So this is multiplication by PB. And this right here is, I think we should call this T sub B maybe. It's the B matrix for T. And I keep thinking, and I'm actually really glad that we're looking at this problem, because I keep thinking that in the book, they simply tell you a formula. Now that I'm looking,
I think I had the formula for if it was from one vector space to a different vector space, but from R2 to R2, I think the only thing it says is if A is diagonalizable, the B matrix is diagonal.
well, we should know. I mean, it's R2 it is a specific case, but it is just a vector space, right? And so we have this formula that applies to all vector spaces. I don't know if I really want to. Oh, in the book they use this notation. So the square brackets is like kind of projecting it down to this. I shouldn't use the word projection, but it's like it's the coordinate transformation. It's the one that gives you the coordinates, and so there's a matrix transformation as well. I think they're basically doing exactly what I was going to do. So if we want this matrix, we want to take maybe I'll go through the details in the same way that they do. So if we have this transformation, and linear transformation, and it's on an arbitrary vector, so we're writing it as a linear combination of the basis vectors. So this is by linearity. This is the linear combination of the transformations of the basis vectors. And now, if we want to figure out, so I'm using the B1s, let me change this. Because we're already using B for something else, so for the basis for this point of view. So I'm going to use E's, since this is our standard basis. And then, if we want, let's call this T of X. So, T of X with respect to our basis B is square brackets of this thing. And because this transformation, this is a linear transformation itself, we have A1, T of A1, dot, plus AN, T of EN, sub script B. And so we can rewrite this as M times T of E1, B to T of En, respect to B. This is a matrix times A1 down to AN. And that's the matrix. Why am I so confused about this? That's exactly what I wanted. I was right the first time. So we do want this in terms of the standard, in terms of the second basis. And so this is the representation of X with respect to that basis. So we do this, and this is a matrix, and this one. So the transformation with respect to that basis of this element is equal to this matrix times the coordinates of that with respect to that basis, and we get the columns for it like this. So we would need to figure out what the representations of A times this and A times this are in terms of the basis B. The basis B. So that involves taking those vectors and translating them into that basis. That doesn't seem like less work than what I was going to do. So I'm just going to do what I was going to do. Are we out of time? We're out of time. I mean, we're out of time. You can leave whenever you was gonna do it in terms of this diagram. So this is PV inverse, and this is the, I'm gonna call this M. You know, in the exam, for some reason, I wrote it as this, and so I'm gonna write it like that. Anyway, I give an explanation of what these symbols mean, so it doesn't matter what symbols I use. But this is multiplication by A, this is multiplication by this matrix here, and this is the one we're trying to figure out, right? This is the B matrix of T. And so I can represent this transformation as going into the B basis. I'm writing arrows for the same thing I already had arrows for. So you translate into the basis B, and then you apply the transformation, which is a matrix multiplication of some kind, and then you go back to this basis here. So what we get is A equals, first I apply P the inverse, then I apply PB, and then I apply PB. To clear why I wrote them in this order, when I apply this transformation to a matrix, I'm multiplying this matrix by it first. So that's this, and then this, and then this. So that's the reason the order looks reversed. Anyway, now because, well, these were linearly independent, and therefore this matrix was invertible. Well, it had to be because we wrote the inverse. We get T sub B is equal to P inverse B A B. So now it's just a matrix multiplication that I have, well, it's a pair of matrix multiplication I have to do, and an inverse. So PB is 1, 1, 5, 4. A was 1, minus 1, 1, 3. And now PB inverse, I'll compute the integer part of it first, and then I have to figure out what the determinant is and divide by that. So that's 4 minus 5, negative 1. This is usually where I mess it up, but I haven't messed up any of my arithmetic today. I think someone in here is jinxing me, and they're not here today. Okay, so I'm just gonna multiply this negative 1 into here just to get rid of it. So minus 4, 1, 5, minus 1. And then I'll do this multiplication here. So this is gonna be 2, 2, 9, 7, 0. So 2, 2, 9, and then 12 minus 5 is 7. Okay, feel good about that? Now, so this is 10 minus 8 is 2. We should end up with a 2, 2's on the diagonal? I think so. Okay, so 2, and then 2 minus 2 is 0. Okay, we've got a diagonal, or we've got an upper triangular. So 35 minus 36. And 9 minus 7, so we get the 2's on the diagonal. And it's not diagonalizable, but at least it's upper triangularizable. So we got that much.
So I guess what confused me about this, so what we're doing, the B matrix is just representing the transformation with respect to a basis. That's it. And then what you're saying is you found B by taking going straight across, which is A, which is also T, is the same as taking the scenic route there with that multiplication. And I guess that's just easier to remember than the formula, which is right?
Yeah, I've actually never used this form. I mean, I used it, I had to memorize it long enough just to talk about it in lecture, and then I immediately forgot it, in case you couldn't tell. It wasn't useful to me for anything.
So is that like what you would recommend, just kind of remember the mechanics of this chart and the formulas kind of?
I would recommend to, do as I say and not as I do, and, understand the reasoning behind this. Maybe not necessarily memorize the formula, but at least know where it came from, so that if necessary,
Yeah,
be able to reproduce it.
That was helpful seeing that. So it's like, where they got the formula from, that's in a way kind of applying like change of basis, it looks like, right? Because that looks like the change of basis, but our vectors, T, B, M, and then we're changing it to the same basis.
Yeah, this is a proof that relies completely on linearity. So it's, everything that we did in here is just taking linearity and using it to change from one form to another. So we change from T to, we change from X to its representation with respect to the basis, and then we use the linearity to change, to commute the T inside. And then we use the linearity of the coordinate, what do you call this, the coordinate operation. The coordinate operation, it's linear as well, and so we use that linearity again in order to turn this into a matrix times a vector. So this is entirely in terms of just like kind of shuffling symbols around on the basis of what we're allowed to do because of linearity. I think this is more conceptual, and gives a little more clarity about what's going on in the transformation. But that wasn't what your question was. Your question was, what do I recommend? Which is learn as much as you absolutely possibly can, regardless of if there is any immediate application for it. But yeah, what did we need in order to do this? We needed to be able to, once we got to this step, we took this arrangement of concepts, right? This is some kind of arrangement of concepts and relationships between them, and we transformed it into a matrix multiplication. And then we just computed the matrix multiplication. In order to do that, we needed to be able to produce matrices at all. This is always going to be a matrix because it's a transformation between R2 and R2. If we're transforming into coordinates, then the coordinates are things that live in Rn. But up here, that may not be the case. And so, in this example, the reason that we were able to write a matrix that does the same thing as this linear transformation and this linear transformation is because we were going from R2 to R2. So that's something to keep in mind in this. Yeah? Is that it? Only 201?
I got some studying to do tonight.
All right. It's been fun.